Okay.
Okay. Yes, so welcome you all to this week of BRAC, the Brazilian Center on Representation Theory, or at least it looks so from the two titles that we have today. So they are both young mathematicians. This is the young BRAC. So let me present the first speaker of today, which is Somaye Behzad from the University of Isfahan. And she's going to talk on exterior powers, polynomial rings, and representation of Lie algebras. So please, Somaye.
Thank you, Professor. First, I am very grateful to give me this opportunity to speak in this seminar. Today, I want to give a short report on the first part of my recent work with collaborating with Contiero and Vidal Martins, which is like an introduction to the second part. And it is concerned with some special example of representation of the Lie algebra and endomorphisms of vector spaces on polynomial rings. To officially start the talk, let me first fix some notation. For me, BR will be the polynomial ring in finitely many indeterminate E1 up to ER. And why I am indicating the indeterminate with EI is that if you want, you can look at BR as the ring of symmetric function in R indeterminates, and then EIs would be the elementary symmetric polynomials. Then I consider the typical model of vector space of infinite countable dimensional, which is the ring of polynomial in one indeterminate X. And this vector space, as you know very well, has a natural basis given by powers of X. And I denote it by delta J, sorry. The dual basis of xi, and as you see, I wrote here the relation delta gxa is the Kronecker delta. Then I consider some endomorphism of V, which I call the elementary endomorphism, because if you write the matrices of Eij with respect to the basis xi, what you get is the usual elementary matrices, which has all entries 0 but 1 in the position ij. Now I denoted with GLV the Lie algebra generated by the endomorphism EIG. So it means that any elements of GLV is a finite linear combination of this elementary endomorphism, and this is a sub-Lie algebra of endomorphism of V with respect to the usual commutator. And what I am going to do is to give an explicit expression of BR as a module over the Lie algebra GLV. Think a bit. In fact, elements of GLV are morally matrices, and if you want to give a model structure to BR over GLV, I must figure out how can I multiply a matrix by a polynomial and get again a polynomial. But what is our motivation? Our motivation comes from what Dejimbo-Kashiwara-Miwa did. Dejimbo-Kashiwara-Miwa, for famous great Japanese mathematician in 18, did this representation, which is well known as bosonic vertex operator representation. But what does it mean? The bosonic is just the polynomial ring in infinitely many indeterminate that you can see here is denoted by B, which is a polynomial ring in x1, x2, etc., infinitely many indeterminate. And they realized that first they in fact don't express like so, but then we consider instead of vector space in one indeterminate, the ring of Laurent polynomial. And so it's better, and it has a basis parameterized by integers, the powers of x, but i's are in z. And EIJs are, as the previous case, we denoted by EIJ the elementary endomorphism. And what they did, they realized that B is a GLV module. And for this module structure, they must have a recipe to multiply a polynomial, I denoted by Px, an element of B by Px, a polynomial by a basis element of GLV. And they did this by using of some generating function. The generating function of EIZ, which is denoted by EZW minus 1, is this series. And they realized that the action of the generating function EZW minus 1 on Px is the same as the action of this operator on Px. And so for knowing what is EIJ star Px, this product is the coefficient of ZIW minus J in this expression. This expression, which is denoted by the acronym gamma ZW, is what in the literature called as vertex operator. For the first time, it appeared in the theoretical physics literature. And due to this vertex operator and the bosonic Fock space B, their representation is called as bosonic vertex operator representation. Okay, and now my task is to explain where does such a representation comes from by revisiting some results by Gatto and Salehian, as we did in the first part of our recent paper with Contiero and Martins. Okay, now I'm considering the finite type of this I consider BR to be the polynomial ring in finitely many indeterminate E1 up to ER with rational coefficient, and I consider the vector space QX. And now I want to convince you first that BR is a GLV module, and then I want to compute a generating function of the action of basis element of GLV on BR. This will give us the a description we are looking for, in fact. Okay, to explain this, to explain what is going on, I start by a very trivial case, which is R equal to 1. So we have P1 equal to QE1, and V is the polynomial ring QX. So you can identify it by QE1 by just substituting the indeterminate. So since V, any vector space V, is a module over GLV, but why we have this is so trivial. You take an element here, say phi, for a matrix A, and you take an element of B, and you define phi star B, the module structure, just evaluation of phi in U. So it's trivial that any vector space is a GLV module, and since B1 is morally QX, so we have an induced module structure on B1 as well. But we are pretending we are not aware of this identification, basic identification. Also, you may wonder where is that xi's that appear in the Degenerations representation. Now I define for you these xi's. These xi's you see here are the same determinant that you see in the representation by Degenerations. I consider the generic monic polynomial E1z of degree 1, which is 1 minus E1z. And I define xi's through this equation. If you compute, what you get is this: x1 is E1, x2 is E1 square over 2, e3 is E1 cube over 3, etc. So xi is the power of E1 over I. And mind that in this case, just x1 is linear algebraically independent, and the others are the power of xi over I. We can make V to be a B1 module by this definition also. We take xj, an element of B, basis element of B, and we define the multiplication of E1i, and a basis element of B1 to be xi plus j. In particular, xi can be reached by multiplication of x0 in E1i. Eij's is as the usual in the previous slides, the elementary endomorphism. Now we want to know how it acts on a basis element E1k of B1. First, we evaluate it against x0, and we define this product like so: xi, because Eij was this, xi tensor delta j, acting on E1k x0. This is an element of B. So by modular structure, this is xk using this. And so you see that what we get is xi delta Kronecker of kj. If you want to act on E1k by generating function, you have the same argument, but you must sum, and the sum ranges over I and j bigger than or equal 0. So you see that here the only term survive is when j is equal to k, and you have just w minus k. And we put it out of this series. What remains is xi, sum of xi, zi. Also, we can use the modular structure to write xi as this form. But in any case, this part for the time being, we will denote it by sigma plus cx0. Just is a notation for the time being, but in the sequel, you will see that it is more than a notation, and I will explain it better to you. Okay. Here you see that we are finished, but since this k appears here, and for some aesthetical reason, we want to get rid of appearance this k. This formula is dependent in this k, and we don't like that. So we decided, instead of acting on a basis element E1k, we act on a generating function of E1k. We consider this series, this generating function, by put one more indeterminate t, and we act on the generating function by evaluating in x0. As the previous argue, we have the sum of k bigger than equal 0 of this expression. W minus ktk is the rational form of this series is 1 over 1 minus t over w. And if you remember our notation, sigma plus cx0 was the sum of xi's, and we can use the modular structure of b over b1, and we have this expression. So this part can be written as sigma e1i zi. And again, this series can be written in this rational form. And up to here, if we work on Z, we are done. But since we are working on Q, and any invertible formal power series is exponential of its logarithm, so we can write both this expression as this exponential form. And if we use the exponential property, we can compact this formula as this. Okay, we find this nice formula and mind that as a conclusion, Eij star E1k is just the coefficient of Zi W minus JTK in this expression. We didn't need to do that, but we are doing because in the sequel, we want to do in the general case, and it's better you see what is going on. Okay. Up to now, we did two extremal cases. The Jimbo-Kashiwara-Miwa representation, which R was equal to infinity, the case R equal to 1, and now we want to know what is in the middle. Not to complicate the exposition with unessential technique parts, I will consider the case R equal to 2, because if you know what is going on in this case, you will understand other cases in general for any R. So first, let me say you that P2 is the set of all partition of lengths at most 2, and lambda 1 is bigger than equal to lambda 2. Then I introduced you the generic monic polynomial E to Z, which is 1 minus E1Z plus E to Z squared. And as the case, as we did in the case R equal to 1, we define X i's, the indeterminate X i's through this equation. But the difference is that in this case, X1 and X2 are algebraically independent, and X1 and X2 are algebraically independent, and other Xi's, X3, X4, etc., are explicit polynomial in X1 and X2. Okay, by this definition, we can write 1 over E to Z E to W in as the multiplication of this exponential, and using the property of exponential, we can write it as exponential of Xi, Zi plus Wi. But Zi plus Wr is symmetric in Z and W, so all this expansion, since we know that Schur polynomial form a basis for symmetric function, can be written as a linear combination of Schur polynomial, and the coefficient we denoted it by calligraph called S lambda x, and is again called Schur polynomial, and lambda range over the T to the partition of lengths at most R. And it is well known that this S lambda x form a basis for B2. For instance, you can look in the book of McDonald's symmetric function. Okay, now I'm using this very well-known fact that B2 is isomorphic with the second exterior power of B. In fact, in general, we have isomorphic between BR and wedge R, BR's exterior power of vector space V. Because, in fact, both of these vector spaces have a basis parameterized by partition of lengths at most 2. I mean, this is isomorphic with QP2. Also, wedge 2V is isomorphic with QP2. So there is an isomorphic, at least between these vector spaces. But the isomorphic we are using is the isomorphic sending the basis element of B2 to a basis element of wedge 2B. I mean, you take S lambda, lambda 1, lambda 2x, which is basis in B2, and the isomorphic image in wedge 2B, we denoted it by this. This is a notation, and this notation means x2 lambda, which is a short way to write x1 plus lambda 1 wedge x2, which is a basis element of second exterior power of V. But why I am doing that? Because if I convince you that wedge 2b is a GLB module, then via this isomorphic, by using Hilbert, we have an induced module structure on B2 also. So let me show you how we can say that R's exterior power in general, and here wedge 2b is a GLB module. In fact, exterior power of V, exterior algebra of V, wedge V, is a GLB module. But how? By using this delta. We take an element of GLB, say phi, and we associated to this phi a derivation of endomorphism of exterior algebra. Since, let me write better. Hello. Hello.
Somaye?
Do you hear me?
Yes, we do. I do at least.
Okay, may I continue? Because
yes,
I thought it is freezing, and you can write. You can see what I am writing here.
Yes, I can see it and I can hear you.
Okay, okay, thank you.
Yes. Mm-hmm.
And since exterior algebra is direct sum of exterior powers, and any element of exterior power is a linear combination of, for example, we are in wedge 3b, we have linear combination of terms in this way, u1, u2, u3. This ui's lives in V, the first exterior power. V is wedge V, wedge 1V is V. So it's enough, we define this delta phi in the first exterior power, which is U itself. And we define delta phi U to be the evaluation of phi in U for any U in B. And for the other elements in exterior algebra, delta phi must satisfy in Leibniz rule. Okay, you can easily check that delta is an algebra homomorphism. It sends bracket to bracket. I mean, the delta of the commutator of phi and psi is the commutator of delta phi and delta psi. Since delta sends the first degree to the first degree, it preserves the first degree, and so it preserves all the other degrees of exterior power. So delta, we have this property that delta preserve, I mean, delta wedge KB is landing wedge KB again. And if we restrict delta phi to case exterior power, is an endomorphism of case exterior power. So then we conclude that case exterior power of V is a GLB module. Okay, so up to now, we conclude that wedge 2V, because we are considering, R equal to 2. Wedge 2V is a GLB module, and since it's isomorphic with B2, B2 is a GLB module as well. And like the other case, we would like to see how a basis element of GLB acts on a basis element of B2. First, we evaluated in X1 wedge X0, and we defined, this is the definition. We define it because Xi tensor delta J was an element of GLB. We do, by using that delta I introduced in the previous slide, we associate delta Xi tensor delta J, and we define this to act on S lambda X, X1 wedge X0. That we learn to write it in this way, X1 plus lambda 1 wedge X2. Here you should write Leibniz rule. If you compute, if you write and compute, you can see that this is nothing but Xi wedging with this contraction, that we can define it also in this way. This is our way to define the contraction. But also I wanted to remark you what we mean by a contraction of a vector in which are we by a linear form. This is so easy. First, sorry, I should put here phi, not psi. In the first row, you just evaluate phi against V1 up to VR, and in the second row, you just put the vector component of the vector V1, V2 up to VR, and then you use the determinant rule. You consider P, phi V1, and then eliminate this row and this column, and you have the wedge product of this, and you do this up to end. For example, if you want to know what is the contraction of this vector against delta 4, we put delta for x4, 5, delta for x4, and delta for x1 in the first row, and the second row we just write x5, x4, and x1. Then we compute. First, you notice that this is 0, this is 1, and this is 0 as well. So what we get if we eliminate these according to the determinant rule, we have minus x5 wedge x1. This was just a remark to remember you what we compute the contraction with our notation. Anyway, so we understood how we can act by an element of GLB on a basis element of B2. Now we are going to now how we can act by generating function of this basis element on a basis element of B2. We do the same yoga. We evaluating x1 with x0. We have this summation. We use the definition, our definition, and we know that this is our way to write x2 lambda, lambda 1, lambda 2, and you remember that our definition sigma x I z I was the sigma plus cx0, and sigma delta j w minus j, I forget to write here for you, we consider as delta the generating function. We consider with the notation delta w minus 1 that you are seeing here. And as you saw, this is our definition. This is why our definition is this, or equivalent with this determinant. And it is enough we know how delta w minus 1 acts on xj. And you know that this is a generating function, and the only term survived is when j is equal to 1 plus lambda 1. So we have w minus 1 minus lambda 1. Similarly here, we will have w minus lambda 2, and we write this term as usual. Now, mind that up to here, I used sigma plus cx0 just as a notation. But for us, it's more than a notation. It's what Gatto Salehian, for example, in the book Hase-Schmidt derivation and Grassmann algebra, called it as Schubert derivation. And now I'm going to explain very quickly what we mean by Schubert derivation. Schubert derivation, which is denoted by sigma plus c and sigma minus c, are the unique Hase-Schmidt derivation on exterior algebra. By Hase-Schmidt derivation, we mean the linear map on exterior algebra to the formal power series with coefficient in exterior algebra, with respect to the wedge product. I mean sigma plus c u wedge v is sigma plus c u wedge sigma plus v. This is the definition of Hase-Schmidt derivation. And Schubert derivation are the unique Hase-Schmidt derivation on exterior algebra such that they act on a basis element of V just by multiplication in xi. You see delta I xj's is xi plus j. Mind that these delta i's are endomorphism of exterior algebra. Delta is belongs to end which we. Their inverse in formal power series with coefficient endomorphism of exterior algebra, respectively denoted by sigma plus bar z, sigma minus wz. You can find many details in the book I mentioned already, but in particular, I summarized here their action on a basis element of V because I need in my computation, especially the action of sigma plus z xi is xi minus xi plus 1 z. Okay, here you see the computation again. And first I use, if you remember, look at the last expression. I factorize sigma plus c since it's a Hase-Schmidt derivation. We can factorize it and we will have here x0 with sigma plus bar z, which is the inverse of sigma plus c. If you apply, because it's respect to the wedge product being a Hase-Schmidt derivation, what you get is sigma plus c x0 wedge. This determinant is exactly what you are seeing here. So we factorize first sigma plus c and put its inverse here. Then we use the fact that it is a Hase-Schmidt derivation, and so you can filter it inside the indeterminate. If you extend, you can see what I am saying. And we then use the definition of sigma plus c xi that I mentioned here. This one. Let me write by another work. Here you can see that if we factorize minus c, we will have xj plus 1 minus xj over z, which is exactly the definition. We have minus c here. And this is sigma minus bar z xj plus 1 by this definition. Okay, so we put this property here. For this and this we use. And what more is that we can factorize this minus z outside of determinate. And then we have one minus sign here. Then we change the order of x0 with this indeterminate. Then 1 minus again appear and kill the previous one. So we have this expression. And if you compute this wedging with x0 is nothing but this determinant. And then we use the fact that sigma minus bar z is identity on x0. This, all these elements have sigma minus bar z, and being a Hase-Schmidt derivation, we can factorize sigma minus bar z, putting outside. So what we get, this expression, which also I can factorize w minus 1 in the first row, and I will get this expression z over w, sigma plus c, sigma plus c, sigma minus bar z, multiplied by this determinant. Okay. Here you see that I got a representation of GLB on B2 by using of the sigma plus c, sigma minus bar z, and these are defined on exterior algebra. And if I consider the evaluation on BR is an element of BR. And when you evaluate against XR0, you land in exterior algebra, R's exterior power. And when R goes to infinity, this expression tends to this, which is called the classical vertex operator. This is the part of the title of my talk. and the other part is concerned with the other parts. But the point is that, as we did in the case r equal to 1, as if you remember, we had a k and we want to get rid of dependence of the formula by this k, and we wanted to kill that. So then instead of acting on a basis element, we acted on the generating function of that basis element e1 k tk, if you remember. We want to do the same here. And instead of acting on one basis element, we consider the generating function. And using some non-trivial techniques, we obtain that the action is the expression you are seeing here. For more detail, please look at the aforementioned paper of me, Andre Contiero, and David Martins, because if I want to go to the detail, I cannot stay in 40 minutes, I think. And that's all.
Okay, Somaye, thank you very much. So let's thank the speaker. Okay, so are there questions?
I think I have a question.
Okay, go ahead. Oh.
So there's something I think DJKM from the finite case. I don't remember if it's possible.
I think Renato is speaking, but
yes, it's hard to hear you, Renato.
Hear you, Professor Renato. May I ask you, please, if there is some noise that I am not able to hear you.
He was cut off. He's frozen now.
Has to do with the finite type, but I didn't understand the question because I couldn't hear very well.
Yeah. Do you want to write it down, Renato?
Can you hear me?
Yes.
Yes.
Now, yes.
Now I hear you.
No. No. Well, no problem.
No, please tell me.
No, it's something I forgot. I mean, can you hear me now?
Yes, yeah.
Yeah. No, how to, recover DJKM from the finite case? I mean, if it's possible, I forgot about it.
You see here that we have BR, which is the polynomial ring infinitely many indeterminate. When R goes to infinity, we have we have infinitely many indeterminate. And in fact, since BR is isomorphic with wedge RV, when R goes to infinity, we have B infinity here, which is the bosonic space, and wedge infinity, which doesn't make sense, and then we land in fermionic space. Yes.
Yeah.
And then we recover the representation by Dejin, Kashiwara, and Niva.
Yeah, right. I forgot.
Okay. Are there more questions? Okay, so if not, let's thank Somaye again. And let's prepare for the second speaker now. So can you stop sharing, Somaye?
Yes, sure. I'm not able that maybe.
She's going to share, to stop sharing.
Yes.
Is it stop?
Yes, I think so. So Eduardo, can you start sharing?
Yes. Yes. All right.
Maybe
Can you see properly?
Yeah, maybe it's still too big. Can you put at least it in a window, on a smaller window, maybe,
Let's see.
instead of using your whole screen?
Like now?
Yeah,
No.
this works. It's probably not the best, but
Let me try another way, please. Share screen. Probably this one. Share. Now it's better or not?
yes, it is. Now we can see the full slide.
All right.
Okay. All right. So let me present the second speaker of today. That will be Eduardo Vidal from Impa. And he's going to talk on degenerations of linear series to curves with three components using quiver representations. Yeah, there's a lot of echo. That's true.
In my microphone?
No, it's probably mine. I will deactivate mine, so maybe that. So please go ahead, Eduardo.
All right. First, thank you for the organizing by the invitation. This presentation is a joint work in progress with Eduardo Esteves and Renan Santos. All right. All right. In 2017, Brian Osserman essentially made the following question to my collaborator Esteves in a private message. Do limits of linear series and curves with more than two components have simple bases? Well, in the end of the presentation, we will see the importance of this question. All right. For non-negative integer d and n, let Zn plus 1d be the points d0 to dn of Zn plus 1 with the sum of di equal to d. And let u0 from un be elements in Zn plus 1, 0, so that n proper subset of them is linearly independent over Q, and their sum is equal to 0. Then, to element U in Zn plus 1d, we associate a quiver Q, depending on U, U0, and U from UN, whose set of vertex is G equal to U plus Z0 until Zn inside this set Zn plus 1d. And whose set of arrows A decomposes a union of AI inside the G times G, such that an arrow from W1 to W2 is in AI for I from 0 to n if W2, the end of the arrow, is equal to W1 plus UI. Right? Then this quiver Q is a Zn quiver, right? But more generally, a Zn quiver will be defined now. So let Q be an quiver and n natural number. Zn structure on Q is a decomposition of the set of arrows in n plus 1 subset satisfying the three following properties. 1. For each vertex V and each I from 0 to n, there is a unique arrow in AI leaving this vertex. All right. Now, for each path gamma in the quiver, let gamma I be the number of arrows of AI that it contains. All right. Thus, if gamma I is equal to 0 for some I, then you call this path gamma admissible, right? Thus, for n2 vertex from V1 to V2, there is a admissible path gamma in Q connect V1 to V2. And the last condition is that for every two paths, gamma 1 and gamma 2 in Q, leaving the same vertex, they arrive at the same vertex if and only if this difference here, gamma 1 I minus gamma 2 I, is constant for each I from 0 to n. All right. And a quiver with a Zn structure is called a Zn quiver. That's the definition, right? The first proposition about it is for each n, all right, all Zn quiver are isomorphic. Well, this is not that difficult to see because when you fix a vertex V, you know that there exists exactly one vertex living in AI living that vertex. So you can think that for each vertex in Zn quiver, you have an arrow leaving and an arrow arriving. So locally it's the same. Fortunately, you can prove that they are isomorphic. Now, this Zn quiver, here we start with the motivation to study this Zn quiver and representation. The Zn quiver arises from the generation of linear series. So let's see be a connected nodal curve with n plus 1 component x0 to xn, and consider regularized morphing pi of C. And by regularized morphing, we mean that the morphism P is flat, projective, the generic fiber of this map is smooth, and the special fiber is isomorphic to C. All right. Thus, let L at be a line bundle of degree D on the generic fiber. And as this, all right, by regular, we mean that this suffix X is smooth. All right. And as X is regular, each component Xi is a Cartesian divisor, and there exists an extension L of L at to the real surface. For each divisor D equal to the sum of NIXI, the sheaf LD, defined as the L tensor or D, is also an extension of the sheaf L at on the generic fiber. And thus you still take UI and U being the multi-degree of or xi for each I from 0 to n and L respectively. You set LV as LD, all right, where V is equal to U plus the sum of n IUI, and this V is precisely the multi-degree of LV. And it's enough to note that this V, this new degree, is inside Zn plus 1 of D. Now, for this divisor equal to the sum of NIXI, which n at the minimum of n equal to 0, give us a natural map, which is non-zero when restricted to the curve C, given by L from V1 of L to V2, where V2 is equal, we denote by D dot V1, in use of the intersection product, is equal to V1 plus the sum of NIUI. So the composition of a map phi from V1 to V2 and V2 to V1 is just a multiplication by Tn, all right, where n is the maximum of this Ni. Now, when you define LV as the restriction of LV on the suffix X to the curve C, then the map phi from V1 to V2 in this, another map from LDV1 to from LV2, now in the curve C, and you keep denoting it by phi from V1 to V2. Right? Here it has an abuse of notation. And now, if for effective divisors D1 and D2, you write D as the sum of D1 and D2, then you have that the map from V1 to V3 is the composition of the map from V1 to V2 and from V2 to V3, where V2 is equal to D1 dot V1. Here's the definition of the dot. And V3 is equal to D2 dot V2. Well, all right. Now let V eta be a subspace of global section of L eta in the generic fiber, X eta. And for each extension LV of this L eta, there is an extension VV of V eta given by the global sections of LV on the surface such that the restriction to the generic fiber is in V eta. The map from V1 to V2 induces a new map, which will keep denoting with Bluetooth notation by phi from V1 to V2 of V from V1 to V2. Now you take the VV as the restriction of VV on the surface restricted to the curve C as the space of global section of LV, then 5V from V1 induce again a map. We'll keep denoting by 5 from V1 to V2 from the subspace vector space now V from V1, V2. Now, thus we obtain a special representation of the Zn quiver Q of U0 to UN, which we'll call an exactly linked net of vector space of finite support. More generally, let Q be a Zn quiver. A linked net of vector space G is a curved representation of Q of pure dimension, satisfying the following three properties. The first is, if gamma 1 and gamma 2 are two admissible paths connect the same two vertex, then phi gamma 1 is equal to phi gamma 2. And if gamma is a non-admissible path, then phi gamma is equal to 0. And finally, if gamma 1 and gamma 2 are two admissible paths leaving the same vertex, such that phi 1 I is equal to 0, or gamma 2 I is equal to 0 for each I from 0 to n, then the kernel of the map phi gamma 1 intersection the kernel of phi gamma 2 is equal to 0. All right. And thus, given vertex V1 and V2 of the quiver, we will write phi gamma equal to V1 to V2, because since gamma is admissible, they depend on of the initial vertex of gamma and the terminal vertex of gamma. Thus this notation. And a path gamma with gamma I smaller or equal to 1 for each I is called simple. Then you say that a linked net of vector space G is exact if for each V1, vertex V1 and vertex V2 in G connected by a simple path, the image of the map phi from V1 to V2 is equal to the kernel of the map phi from V2 to V1. And you say that a linked net G has support on a subset H of G if for each W in G there is a V in H such that the map phi from V to W is an isomorphism. And if H is finite, we say that G has finite support. And finally, you call a collection of vertices from V1 to Vm in G and vectors Si in VVI for I from 1 to n, such that the image of the map from V1 to V of S1 until the image of the map from VM to V SM generates the space VV for each vertex Q of Q. It's a set of generator, all right? And if M is equal to the dimension of the linked net G, the set is called the simple base of G. Now, when the path gamma is simpler than decimal admissible, phi gamma is determined by its initial vertex V and by the set L, which are the I for which gamma I is equal to 1. Thus, we write that phi gamma as the map starting from the vertex V along L. All right. And exact linked net of vector space of Zn quiver satisfies the intersection property if for each vertex and collection L0 to Lm of subsets of from 0 to n, you have that as the sum of the kernel of the map from V, from the vertex V, along Li with intersection with the kernel of the map starting in V along L0 is equal to the kernel of the map from V along Li intersection L0. All right. You know that the intersection of this kernel with this one is precisely this kernel. Thus, this equally is like distribution law for intersection of vector space, which is not true in general, because in general. And here a theorem that exact linked net with finite support admits a simple base if and only if it satisfies the intersection property. All right. So what this theorem says, when a exactly linked net admits a simple base, it means that this linked net decomposes as subnets of dimension 1. So in general, exactly linked net admits a simple base is a global condition, and B satisfy the intersection property is local condition in each vertex. All right, so you are characterizing a global section with a local property. All right, it's if and only if. So here we give an idea of the proof. Now, in the first direction, if an exactly linked net with finite support admits a simple base, then it satisfies the intersection property, right? This proposition is not difficult because when the linked net admits a simple base, you can describe that these kernels, with some set condition. And to prove the proposition turns out to use essentially set theory, right? To prove the converse, you proceed by induction on the dimension of G, right? And now this proposition, right, which is essentially the most difficult part of the proof, and says that if the linked net G is exact of finite support, then there is a vertex U of Q such that the quotient, this quotient is non-zero. All right. And what this means? This means that you take the sum of the image of the maps phi alpha, with alpha being a path with terminal vertex equal to U. All right. And if G satisfies the intersection property, given a vertex U as above and S in VU minus the sum of the image of phi alpha, the subnet age of G generated by S, and the quotient represented exactly linked net G over J are exactly linked nets satisfying the intersection property. All right, essentially here is the step of induction, this proposition. And all right, now H has a simple base given by U, and S1 is equal to S. And since the quotient G over H has dimension equal to n minus 1 and satisfy the intersection property, by induction, the quotient admits a simple basis as well. Yeah. And so you take beta 1, B1, a simple base of H, and beta 2, B2, a simple base of the quotient G over H, respectively. Thus, with a easy and standard verification, we conclude that S1 to Sn is a simple base of G. Okay. Here, an example to illustrate the theorem. All right. An exactly linked net of vector space over Z2 quiver with finite support on that triangle quiver Q delta admits a simple base. Well, here Q delta is this triangle in red with the vertex V0, V1, V2. All right. Since this representation assumes that has support on Q3, all right, we have isomorphism leaving these three vertices V0, V1, V2, which is in blue. Each blue arrow is an isomorphism here. The green ones are 0, and the black ones can be anything between, not necessarily isomorphism or 0. All right. Thus, we can verify the intersection property in these three vertices V0, V1, and V2. All right. And by a theorem, this linked net of vector space, which has support on this Q delta quiver, admits a simple basis. All right. All right. Here we will define a new object. Thus, given linked net of vector space G over Zn quiver Q with support on a finite subset H of G, the linked projective space LPG H is defined as the points of the product of projective space VU with U in the support H, such that the image of the map from V1 to V2 of SV1 wedge S2 is equal to 0 for each arrow from V1 to V2 with V1 and V2 in the support H. All right. Thus the theorem is, let G be an exactly linked net of vector space with finite support over a Z2 quiver. Then the linked projective space LPG is Cohen-Macaulay, reduced, connect, and has pure dimension R. Observe that here the LPG depends on age, all right? Here you did not put age because when age satisfies some condition, not very difficult, a simple condition, this LPG does not depend on age, all right? So there's a huge set of support which give us the same LPG. Because of that, you do not write age here. All right, here an idea of the proof of the theorem. All right. that for each vertex U of the support, we will define LPG U star as the point of LPG such that the map from U to V of SU is non-zero for all V on this V is in age, all right, in the support age. Thus, this is an open set isomorphic to the open set of the projective space of VU. Hence, it's reduced, non-singular, and reduced by dimension R. And if it's not empty, because if there exists some map leaving U and is equal to 0, this LPG star is empty. All right, does it's empty to satisfy all this condition. Then we define LPGU as the closure of LPGU star, the closure inside the LPG, and use this theorem that says that if when G is a linked net of vector space of dimension 1 with finite support over Z2 quiver, G is generated by a triangle. What does this mean? It means that there exists a triangle which you can pick one vector in each vertex this triangle, and these three vectors generate the linked net. All right, here is a theorem that essentially characterizes the points of LPG and says that if G is exact with finite support over a Z2 quiver and U, V, and W vertex of a triangle, then the following three statement holds. The points S of LPG, which are minimally generated by a single vertex U, form the dense open subset LPG star U of LPGU. All right. The points S in LPG, which are minimally generated by the segment UV, essentially generated by two vertex, form a dense open subset of LPGU intersection LPGV. And the points which are minimally generated by the triangle UVW form the whole intersection LPGU intersection with LPGV intersection LPGW. So essentially you must think that given a point in LPG, it's generated from one vertex, two vertex, or three vertex. Thus, it follows that LPG star defined as the union of LPG star V, which is not difficult to see that is adjunct union, is simple. It is dense in LPG, thus LPG is generically reduced of per dimension R. Now it's enough to show that LPG is Cohen-Macaulay because Cohen-Macaulay generically reduced will imply reduced, and which we can show by proving that LPG is locally given by the right number of independent equations in the product of projective space, right? So our task now is to count the number of equation, the defining equation of LPG, and show that it has the spectral coordination. So this step one. Step one essentially will prove the theorem to a Z2 quiver with finite support and a triangular quiver. Thus, use this to conclude the general theorem. Thus, using that exactly linked net of vector space with support on a triangular quiver, Q delta, admits a simple base, as you saw in the previous example. We'll consider C, the this represents this exact net, which is over Zn quiver, but here we just draw the support. We are assuming that support in a triangle quiver. All right. For each VI, decompose as VI equal to VI0 plus VI1 plus VI2, where VI0 is the subspace of EI generated by the vectors of the simple base, which are in V0 and analogs for the world, VI1, VI2. And thus, with this decomposition, the maps become diagonal with the 0 and 1s in the diagonal. All right. And you define pi ij from Vi to Vij as the projection, and set the Dij as the point of LPC for which this projection Pij of Si is non-null. Right? Then you can show that the LPC is covered by the opens D01, D12, D02. And on each of these open sets, these three here, we count the number of dependent equations among the defined ones of LPC to obtain 2R, which is the expected codimension. Because here we have essentially, we have 3 PVI, which has dimension 3R. We have LPC, which has dimension RR. And the codimension is the expected one equal to 2R. Then LPC is Cohen-Macaulay, thus reduced, and has proof dimension R. The step 2 is the following. Using the classification of the point of the linked projective space, for each point X now on the linked projective space of the general linked net G with finite support and exact, we find an open neighborhood UX, or shorter of this X, isomorphic to an open subscheme of LPCX, where the CX is a certain exactly linked net with finite support on the triangle quiver. Thus, you found an open neighborhood of X, all right, as we wanted, all right, with finite support. Then you conclude that LPG is Cohen-Macaulay and reduced, all right, because we found the open neighborhood of X, which is isomorphic to open subscheme of Cohen-Macaulay scheme. Thus, we conclude that LPG is Cohen-Macaulay and reduced. Now, we talk further question of this work, right? And when the limit curve C is of compact type with the components, the corresponding quiver Zn, Rocha proved that the multivariate Hilbert polynomial of LPGH is equal to the multivariate Hilbert polynomial of the diagonal of inside the product of projective space, right? And the conjecture with states that the linked projective space LPG associated to exactly linked net of vector space with finite support on H over Z2 quiver has multivariate Hilbert polynomial equal to that of the diagonal inside of the product of projective space, right? Just we said that this is true for a Z2 quiver. And when G arises as a flat degeneration, which the case if G admits a simple base, no, or arises from a degeneration of linear series, the conjecture is true. So here we see the relevance of the question raised by Osserman. We conclude that if G admits a simple base, then the conjecture is true. And we already found an example showing that the question of Osserman is not true in general. So we found a limit of a linear series, which gives us an exact enough to space, which does not limit simple base. It's all. Thanks.
Okay, Eduardo. So thank you. Let's thank Eduardo. Okay, are there questions? Okay, so maybe Eduardo, I can mention that this is a joint work with Renan, myself, and Eduardo. And we're doing some work together with also Oliver Lorscheid in extending the results that we obtained here to any ZN quiver. So the Cohen-Macaulayness and these past results are just for Z2 quivers, but we hope to be able to extend it. All right, so if there are no comments or questions, so let's thank Eduardo again.
So I can stop sharing.